What is polypropylene or PP? Polypropylene or PP is a thermoplastic polymer produced by catalytic polymerization of propylene. It uses the coordination catalyst, which is Ziegler-Natta catalyst. It's also a highly versatile, low density and cost-effective polymer and one of the most widely used plastics globally. Let's look at the types of polypropylene in the industry currently. So there are three main types. So the first is the atactic PP, secondly is the isotactic PP, and thirdly is the syntactic PP. So we will be choosing the isotactic PP because it is the most commonly produced throughout the world. For the feedstock, it consists of propylene, which is obtained from steam cracking, the Ziegler-Natta catalyst, the co-catalyst, which is the alkyl aluminum compounds, and also hydrogen and nitrogen. In the following slide, there will be the details of the process conditions and also the compositions. These are some of the key properties of PP and propylene, which will be used in the process and also for the calculations.
This is the synthesis route for polypropylene. Polypropylene is produced by addition polymerization of propylene, an exothermic reaction that occurs in the presence of catalysts such as Ziegler-Natta or metallation catalysts. The overall process starts with raw material refining, where propylene is purified and stored as a liquefied gas. It then undergoes polymerization in a reactor, followed by cooling to control polymer growth. And finally, the polymer is pelletized, while unreacted gas is recovered and recycled to improve efficiency. For polypropylene, we have four types of polymerization. First is the gas phase polymerization, where propylene reacts in the gas state on solid catalyst particles, forming polypropylene as a dry powder. The reactor used is FBR because it provides excellent gas-solid contact and efficient heat removal, and this route is the most widely used in modern polypropylene plants. Second is the slurry polymerization, where propylene reacts in an inert liquid diluent with polymer particles suspended in the liquid, and the reactor used are loop and CSTR because loop reactors provide good heat removal through high circulation, while CSTR offers stable mixing and temperature control. Next is the bulk polymerization, where liquid propylene acts as both the monomer and reaction medium, eliminating the need for solvent. The reactors used are loop and CSTR because loop reactors efficiently remove heat, while CSTR allow better control of residence time. And after reaction, unreacted propylene is flashed and recycled. And the last one is solution polymerization, where both the monomer and polymer are dissolved in a solvent at high temperature. The reactors used are CSTR and PBR because CSTR provide uniform condition, while PFR allow precise residence time control. In conclusion, gas phase polymerization using a fluidized bed reactor is the most commonly used industrial route. It avoids solvents, reduces separation steps, and produces dry polymer granules efficiently, making it ideal for large-scale production.
So for this part, I will explain the reaction system, catalyst use, and the reaction kinetic involved in polypropylene production. Polypropylene is produced by slurry polymerization using Ziegler-Natta catalyst in the CSTR because it provides good mixing and operate under steady state condition, which means temperature and composition remain uniform throughout the reactor. Next, the polymerization takes place on active catalyst site because the reaction follow a coordination polymerization mechanism. There are no free radicals involved, therefore radical termination is negligible and chain termination mainly occur through chain transfer reaction. We also assume complete back mixing in the reactor to ensure uniform concentration of monomer, catalyst and drawing polymer chains, which allow the rate law to be expressed directly in terms of reactant concentration. Now, I will briefly explain the reaction step involved. First is initiation. In this step, the propylene monomer coordinate with an active catalyst site to form an active polymer chain. This step is relatively slow and control the formation of new polymer chain. Next is propagation, which is the main polymer growth step. Here, propylene monomer continuously insert into the growing polymer chain. This step dominates the overall reaction rate and is responsible for increasing the polymer molecular weight. Then, we have chain transfer reaction, which limit chain length. Chain transfer can occur either to monomer or to hydrogen. Chain transfer to monomer produce that polymer and regenerate an active catalyst site, while chain transfer to hydrogen is commonly used to control molecular weight in industrial processes. Finally, catalyst deactivation occurs. Over time, active catalyst site gradually become inactive, reducing the overall reaction rate. Because these steps are assumed to be elementary, the rate law for each reaction is written using the law of mass action, where the rate depends directly on the concentration of the reactant. From all reaction rate law that we have obtained, we can write the net rate law for each species. The net rate law is then obtained by summing all the formation terms and subtracting all the consumption terms. In terms of kinetic, the reaction is carried out using slurry polymerization in a CSTR. Slurry polymerization allows effective heat removal, which is important because polypropylene polymerization is highly exothermic with a heat of reaction of approximately negative 83 kJ per mole. The reaction is typically operated between 60 to 80 degrees Celsius. At higher temperature, catalyst activity decreases due to site deactivation. The activation energy for propagation generally range between 40 to 77 kJ per mole depending on the catalyst type. At around 60 degrees Celsius, the propagation rate constant can reach value as high as 1000 to 2500 liter per mole per second, indicating a highly active. Finally, I will explain how we obtain the rate constant, which is K. The rate constant for each reaction is calculated using the Arrhenius equation. The pre-exponential factor, which is A, and the activation energy, which is EA, are obtained from literature and reported industrial data for polypropylene polymerization with Ziegler-Natta catalyst. By substituting the operating temperature into the Arrhenius equation, we can calculate the value of K for each reaction.
In this project to produce 100 kg per day polypropylene, the most suitable reactor is CSTR, as most industrial polypropylene production commonly uses slurry phase loop reactors, which are also a type of CSTR. It provides uniform temperature and concentration with constant feed and steady state conditions to maintain consistent polymer properties. With the presence of agitator, it allows effective heat control. Unlike batch reactor, it has poor productivity and inconsistent product quality. CFR is difficult to control temperature for highly exothermic polymerization. PBR has a major issue of catalyst deactivation and pressure drop, resulting in CSTR as the best choice in this case among these. The diagram shows the top, bottom, and front view of the CSTR design in the AutoCAD. This diagram shows the dimension of the CSTR design.
For the calculations part, the target is to achieve 400 kg per day of polypropylene production rate. We assume the feed to the system contains 80 mole percent propylene, 19.9 mole percent hexane, and 0.01 mole percent hydrogen. And we assume operating conditions based on the range reported in the literature. The catalyst used is Ziegler-Natta catalyst. The operating temperature is 80 degrees Celsius, pressure is 25 bar. Catalyst feed concentration is 0.1 gram per liter. Hydrogen feed concentration is 0.005 mole per liter. Inlet volumetric flow rate is 0.12 liter per second. Volume of reactor is 50 liters and conversion is 0.8. So first we need to convert the 100 kg per day production rate to molar flow rate in mole per second by using the molecular weight of propylene, and we can get 0.0275 mole per second. And then we can calculate initial feed rate of propylene by dividing the molar flow rate by the conversion. And since the feed is in liquid phase, we can calculate initial concentration of propylene by using the formula F0 divided by V0 and get 0.27 mole. The concentration of active catalyst sites depends on the titanium weight percentage in the catalyst and the fraction of titanium atoms that are catalytically active. And only 1 to 10% of total titanium atoms appear to be active sites. So for our system, we assume weight percentage is 3%, active fraction is 0.1, and we can calculate concentration of active catalyst sites by using the formula catalyst feed concentration times weight percentage divided by molecular weight of titanium and times active fraction. And then we can calculate final concentration of propylene, Ca, by using the formula Ca0 times 1 minus x, and residence times by using the formula V divided. Then from the CSTR design equation, we can determine the final concentration of active polypropylene chain Cb and the final concentration of hydrogen. And then we can substitute all the value we obtain to calculate the net rate of all species. The active catalyst sites A, C, D, E, F, G, and H. And then we can calculate the yield of all products by using the formula the net rate of the products divided by negative Ra. And for the selectivity of polypropylene relative to that polymer, we can calculate by using the formula Rc divided by Re, and we will get 0.97. Here is the MATLAB programming code that we use to simulate all the calculations and generate graphs. And this is the result obtained from the simulations. The graph of yield and selectivity of polypropylene versus inlet volumetric. Initial concentration of propylene and the volume of reactor is plotted to examine their effects towards the yield and selectivity of polypropylene.